today I'm going to talk about pushing block puzzles. This is, for me, a very old topic. It's one of the first problems I worked on together with Joe O'Rourke and my dad, Martin Domain. And we, so that started in 1999 for me. And so I'm going to go down a kind of historical tour of pushing block puzzles and proving them to be hard, starting even before I started in the 90s, and then going through to a new result this year. So the bulk of this will span 25 years, and there's a lot of neat connections between the old and the new. So pushing block puzzles come from video games primarily. There are tons of video games that have pushing block puzzles in them. These are just some examples. Maybe most famous is the Legend of Zelda series and Tomb Raider series. But I grew up playing the Adventures of Lolo on NES and Balderdash on the Commodore 64. Those are some pretty epic pushing block puzzles. This is a partial list of video games that include pushing block puzzles. I'm sure there are many more. There are hundreds of video games that have pushing block puzzles. It's kind of a favorite staple for type of puzzle. So there are many different types of pushing block puzzles. I want to focus on one prototype, and then we'll look at lots of variations. This is one of the first that we looked at. It's called Push-1 or Push-1F. It's called push, meaning you can push a block. So if we look at the left example, if I move over to the right here, so the happy face is my agent or robot, I can push, in the case of Push-1, I can push up to one block at a time. So if I tried to move right again, I would fail because I can only push one block, but there's a second block behind it. I'm not strong enough. So in Push-1, you can only push one block, then maybe I exit. On the right is an actual puzzle to solve. You can think about it for a little bit. The black squares are not movable at all. So if my happy face tries to move left, he'll fail. There's no, you're not able to even push a single black block. They're like really heavy or fixed. But the blue blocks are pushable. And this is sort of the simplest puzzle. I remember seeing it in some Legend of Zelda games. If you tried to directly push this block over, for example, you get stuck and you lose the game. But there is a solution, which is to push in the two side blocks first, and then you can push the other one perpendicular and get out. Okay, now Push-1 and Push-1F are quite related because as soon as you have a 2x2 block here, it's impossible to ever push that. So it's really just a scale factor issue. These two games do turn out to be different, or at least as far as we know. It's a little bit more compact to be able to have a fixed block that's just 1x1. But if you don't need really tight packing, then these two games are basically the same. This game, this Push-1F is in some sense inspired by Sokoban, which is one of the first pushing block puzzles. It exists in hundreds of different implementations and ports, but you see an early one on a CGA graphics on the right, PC gaming, but it surely predates PC gaming. So you can think of Sokoban as Push-1FS. So you have strength 1, you can push one block at a time, you have fixed blocks, but the goal of the puzzle is a storage goal. So if you look at the example on the left, there are these little dots. That's where we need to get blocks. They're unlabeled dots, and the blocks must get to, the goal of the puzzle is to cover each of those dots with a block. And the number of dots equals the number of blocks. So you have to find the matching, and you have to navigate to get the blocks there. And these brick walls here are fixed, and the boxes are movable. This is the Warehouseman. All right, so that's 1984. And so we've seen already one variation of Push-1F, which is the storage version. We'll come back to storage problems a little later, but for the most part, we're going to think of the original version, which is just the robot starts at one location and wants to get to another location. Is it possible? That's the Push-1F. Sokoban was proved PSPACE-complete in 1997 by this guy, Joe Culberson, who was one of the people who solved checkers. This is the Chinook accomplishment in 1992, where they weakly solved checkers at that point. Later, they strongly solved it. So from the initial position, they know they can find a winning strategy. So this was a major breakthrough in 1992, and then I guess Joe Culberson got bored, and he proved Sokoban as PSPACE-complete. And the proof is quite complicated. I'm showing here the high-level architecture, which is to build a Turing machine, and there's this incredibly complicated crossover gadget. We are going to see at least 2 more proofs, simpler proofs that Sokoban is PSPACE-complete today that are more recent. But this is one of the beginnings of analyzing the computational complexity of pushing block puzzles. So brief crash course on computational complexity. Today you will need to know 3 words, mostly just 2 words, NP-complete and PSPACE-complete. These are different levels of computational difficulty. You don't need to know exactly what they mean, but they're probably both different from the usual algorithmic setting, which is we care about polynomial time algorithms. If your problem is NP-complete or PSPACE-complete, probably it doesn't have a polynomial time algorithm, though we don't actually know how to prove that. From a puzzle perspective, there are 2 possibilities. One is that whenever your puzzle is solvable, there is a short solution that you can show someone how to solve it. That's usually an NP-complete puzzle, or that means that your problem is in NP, which is in this complexity. And then if you are NP-complete, you're at the maximum edge of that difficulty, right at that spot. This is a rough diagram of computational difficulty, or the x-axis is computational difficulty. The next level up is this PSPACE-complete. So PSPACE problems are anything you can solve with a polynomial memory computer. And so PSPACE-complete problems are puzzles that require executing a computer and require essentially running for exponential time, we think. We are going to, I'm going to mention NP-complete, which means we're right here, PSPACE-complete, which means we're right here, and NP-hard, which means we're either at this position or somewhere to the right, and we don't know whether we're PSPACE-complete or NP-complete or somewhere in between. Those are the only things you'll need today. So let's add some more variations to push. There's going to be a lot. The first one here is, we've talked about Push-1F, where we can only push 1 block at a time. First variation is, say, Push-2F, where you can move 2 blocks at a time. So you can see after those blocks get coalesced, in the top diagram, it's no longer possible to move them horizontally, but in the bottom diagram, the robot is strong enough to do so. There's still some fixed blocks which are immovable. If we drop the F, those would not be allowed. In general, we have push K for strength K, and we will write push star if you have infinite strength, if you can move arbitrarily many blocks at once. Okay, so here is what I call early history, which means before I started working on the problem in 1999. Maybe not early for some of you, but early for me. I mentioned this result at the bottom, that Sokoban is PSPACE-complete by Culberson in 1998. But in fact, there were a few papers before that one. In particular, there was an NP hardness result for Sokoban, so same problem. That was a few years earlier. But actually, one of the first papers in this area was by Joe O'Rourke here with Daggett. That proved 3 different results about what was later coined push star. Push star is when you can push arbitrarily many blocks. And there are 3 sub-variations here. There's no fixed blocks, which was posed as an open problem back then in 92. This is CCCG 92. There's the F version where you have fixed blocks, and there's a new version, which we will only see here, where instead of just, normally the goal is to find a path from some start point to some destination point. Can you find a solution path? In push star FM, we want a monotone path. In that case, the problem turns out to be solvable in polynomial time. Maybe not so surprising, but it's nice. That's one of the few positive results you'll see in this talk. But without that constraint, Turns out the problem is NP-hard. That was the main result. And they left open this push star problem, but when I write an asterisk next to an open problem, that means it's since been solved, so please don't work on it. But at this historical moment, the problem was open. Okay, so those are some of the first papers. Let's add another variation. The first variation I worked on with Joe and my dad is called push-push. And I'm also going to introduce another variation at the bottom here, push-push-push. I don't know how, maybe you could add a fourth push and it means something, probably. But at this point, we imagine we're pushing the blocks on ice. So our robot is good at walking on ice and doesn't slide around, but the blocks slide around. So in this top example, when the block gets pushed to the right, it slides all the way till it hits another block and then it magically stops. This is a bit contrary to physics, but the idea is the block slides until it hits something. In the bottom example, push-push-push, any blocks that are that you collide with also begin sliding until you hit a fixed block. The only way to stop is hitting the edge of the board or a fixed block. So those are some more prefixes we can add to the game. And then from my perspective, this really got started with this paper by Joe O'Rourke and a bunch of students at Smith, where they proved that push-push 1 in 3D. So just to remind you what this means, the 1 means that you can push one block at a time. There are no fixed blocks in this result, so a little bit stronger to not need fixed blocks. But we have this new slide column, which says that when you hit a block, it slides the maximum amount until it hits something else. The goal is still to follow a path, to find a path from source to destination, and they proved NP hardness for this problem. But they needed to extend the puzzle to 3D. Then my dad and I joined on here, and with the next year, I think through that Christmas time, this is at CCCG 2000, we proved that in 2D, the same result, NP hardness. We'll describe these in a moment. And in this, I guess it was a second paper, we proved the same result for regular push. So push-push turned out to be easier to analyze, which is, we keep introducing variants because they're easier to analyze. We don't know how to solve the original problem. But then we went back to push-K and were able to solve it. And in parallel, roughly the same time, Michael Hoffman, having heard these problems, solved the push star and by accident sort of solved push-push star as well. So at this point, solved in the sense of proving NP hard. The remaining open problem, which we will get to, is which of these problems are PSPACE complete. But for initial hardness, these are all done. And now I will show you some of those proofs. They're all reductions from 3SAT, where you're given a Boolean formula of this shape where you have a bunch of clauses ANDed together, and each clause consists of exactly 3 literals. A literal is either a variable or its negation. And you want to know, can I make this formula true by assigning truth values to the individual variables? So in this example, you can do it. If we set x to be true, that satisfies this clause and this clause, 2 out of 3. And if we set y to be false, then this clause will also be satisfied. Can be satisfied multiple times, that's fine. In fact, once we set z to something, we're going to satisfy these clauses, some of these clauses more than once. We just need at least one of those literals to be true in each clause. Okay, this problem is one of the first second NP complete problem. First paper. All right, here is Michael Hoffman's proof that push star is NP hard. It happens to also work for push push and for push push push. But that maybe wasn't observed at the time, but retroactively it's not so hard. So the robot is down here in the lower left corner, and there's some gadgetry here to where the robot can make some choices and set variables to be true or false. First, it's going to choose whether x is true, whether y is true, and then whether z is true. And then the bulk of the reduction is this little area here. This is keeping track of essentially the the adjacency matrix here between which literals are in which clauses. So there's a 3 by something rectangle for each clause. It has a blank space essentially for each of these literals. So you notice in each of these rectangles there's exactly 3 blank spaces. And then this part will end up being clause checking, but let me show you an example. So here's the robot. It's going to start walking. In this case, it goes in the rows that set all 3 variables to be false. And you can see over here, because each of these blank spaces corresponds to how many times that clause is satisfied. So the first clause is satisfied once, the second clause is satisfied twice, the third clause is not satisfied at all. So by the time the robot gets there, they're stuck. They get so close to the goal. The goal is right here, by the way, but can't actually make it. Whereas if I set the variables in this way, here I set x true, y false, and z true, you can see, if you can see the blank spaces here, there's one here, one here, one here, one here. Every clause has a blank space. And so when the robot gets over to the right, there's this infrastructure here just to force you to visit this in a particular way. You can fill in your choice of blank hole within each one and get to the goal. Okay, so that's a visual overview of that proof. It's very clever. Maybe one of the cleverest proofs here. So then let's go back to the push-push-1 NP-hard in 3D, reducing from the same problem, but here it's more laid out like a graph. There are a bunch of gadgets here for choosing variable values. Here we're kind of drawing just the empty paths that the robot can move. This is the original style. So a robot comes in here, can push this block either to the left or down, and that lets the robot either follow the true path or the false path, and from those can go over to visit the clauses and push these blocks over in order to later, when we check the clause, we're going to come in here, push the block down, and it will slide as far as it can in push-push. So if we satisfied the clause, that's good. If we didn't satisfy the clause, this will go all the way down to the bottom and we'll get stuck. On the right is an example solution path. Okay, high-level overview. But at this point, we didn't know how to make crossover gadgets, so this required a 3D construction, which is a little unsatisfying. I think before we solved that, we solved push-1, or at least I'm going to present it that way. So you can follow the same architecture, exactly the same picture, but I'm going to change, in particular, what clauses look like. So bear with me, this is a little bit complicated because this was one of my first NP hardness proofs. There are much simpler ways to do this, but the clause at the end is going to be this lock gadget, which is a very clever construction I think Marty came up with. And what these 3 diagrams illustrate is that if you first come in here, you can just move this one little block, and that will later, when you come in this way, it will let you exit down here on the bottom, which is what the second diagram shows. It's a bit complicated, but you can get out. Whereas if you try to enter without moving this block down, that's the third animation, you get stuck. You won't be able to get down to the bottom. So this is the property we want. This clause, this lock is remembering whether it was unlocked by some literal. And we have a bit of a leakage issue. We need to connect 3 literals to this one position, this one entrance. And so what we do is this construction, where we have the 3 literals coming in, and the robot is trying to get here. And when it does so, there's this magical gadget in between, which is called a NAND. And it says, well, if you come in this way, you destroy this connection. And if I, for example, if I come in here and follow this path, I will destroy this connection. And then I'll have to go down here and destroy that connection and come down here. So I won't be able to leak into these other wires. Okay, kind of a technical problem, but there's a bunch of gadgets here. This NAND gadget will actually turn out to be really important, so we'll come back to that in a bit, but it's very simple. If you come in here, you prevent later traversal this way, because these 2 blocks are against each other and we only have strength 1. And similarly, if you traverse the other way, then you won't be able to go from west to south. Okay, so that's push 1, still in 3D because we still need crossovers. Then we came up with this really complicated crossover gadget that works for both push 1 and push push. What you're seeing here is 1/4 of the gadget. In fact, there are 4 of them composed in this little matrix. And you can see the lock appears and a few other gadgets. This gadget will actually come up later. Here's another lock. This is a slight variation on the NAND. Please don't build this gadget at home. It's very dangerous, but it does prove NP hardness in 2D. Okay, this is 2000. In modern times, we have many ways to simplify this proof. I'm going to show you 2. One of them is this very nice result by Pills from 4 years ago called linked 3-sat. And it shows that planar 3-sat is hard even when, so you can guarantee that the connections between variables and clauses together with a Hamiltonian cycle that visits all the variables and then visits all the clauses, that whole graph is planar. This is sort of our dream. We always wanted this to be true, and then Pills solved it for us. There are some subtleties about sidedness, but in the end, it would let us follow this proof, except some of the literals would have to come in from the other side, and not need a crossover anymore, because he can give you crossovers for free, essentially. So that's nice. We can throw away this gadget. All right, before I get to the other simplification, I want to describe yet another version of push, where we're almost done through all of them. So this was a variation I remember Joe and Marty and I came up with, maybe with Michael Hoffman. We were trying to find a version of pushing blocks that was easy. And this one is at least easier. It's called push X, X for, X marks the spot, I don't know, X for disappearing. So in this version, as you walk, your walls raise above you in this picture. In most video games, this is actually quite common in video games, there usually the floor is falling, and so you have to move really fast, and as you walk, the previous platform you were on falls down into an abyss. Sort of like this AI art here. This feels easier. In particular, it's guaranteed that the number of moves you make is polynomial. It's linear in the board size. So this problem is definitely in NP, unlike the other games, many of which are PSPACE-complete. But it turns out it's not much easier. All of these games turn out to be NP-complete. So the 4 versions we've talked about here so far are push with infinite strength, push with infinite strength, push with finite strength, and push with finite strength. It turns out for the push star versions, infinite strength, the existing proof that I showed you, the really complicated one with the beautiful sat reduction, it just works because you never actually revisit the path. Or maybe you had to make one small tweak, but it works. However, for the push versions, so where we have finite strength, say push 1x or push 1x, there we needed a brand new proof, which we came up with in the following year. And I'm going to show you that. And this proof turns out to be useful for things beyond just push 1x. So this is a reduction from 3 coloring planar graphs. So you're given a planar graph like the vertices and dashed edges shown here. And we want to assign colors 1, 2, 3 to the vertices so that no adjacent vertices have the same color. So the way we're going to implement that is the robot is going to walk around this red or orange path, which is an Euler tour of the graph, an Euler tour of a spanning tree of the graph. So let's zoom into how that works. As we visit a vertex, we're going to choose. So as I enter a vertex here, for example, we're going to make a choice about which color that vertex is, 1, 2, or 3. Actually, it's probably better to think about entering here. So suppose we enter this vertex U. We make a choice about what color it is. And actually, every time we visit the vertex, we're going to choose what color it is. So we want those to all be the same choice. And we build a gadget here that forces them to be the same, called the consistency gadget. And then as we traverse an edge, we're going to traverse every edge twice, one from one of the vertices and one from the other vertex. We want to make sure those colors are different. And so we've got a gadget here to check that. So there are some very simple things here, like the choice gadget is just one of these forks that we've actually used in previous proofs. There's some one-way gadgets, which are really easy. The bulk of the construction was these color consistency gadgets. So here we have the 3 colors 1, 2, and 3 from each side of the edge. And what we're using here in this little square is the NAND gadget. So what this is saying is if we use color 3 up here, we want to close off this other path so it won't be possible to use color 3 on the other side. So this will guarantee that the 2 sides of the edge use different colors. So that's kind of cool. Similarly, for the consistency gadget, we look at all pairs of colors that are different and we thread them through a NAND gadget. And that will guarantee what we need, which is that the color is chosen the same at each vertex. So here again is the NAND gadget, and we in this proof we used another gadget, the XOR crossover, which we had developed previously for push 1. So this is a bit of a complicated proof. More recently, like just a couple of years ago, we realized this proof simplifies quite a bit in that it all really just can be reduced to the NAND gadget. So it turns out this XOR crossover, if you just replace it with a NAND instead, it works fine. Same proof works. And the one way that I drew before can be implemented with a NAND just by blocking off 2 of the ends. And the choice gadget can be implemented with a NAND by just connecting 2 of the ends here. So if you have a NAND gadget, you can follow this proof and you show that if you can connect the NANDs together in some planar way, that's enough for traversability to be NP-complete. So I'll write this down as a theorem. If you have a planar network of NAND gadgets and you want to know can the robot get from A to B, that problem is NP-complete. And so in some sense, the whole proof that push 1X is NP-complete is this one diagram, this one gadget. So that's pretty cool. This gadget will come up later. All right, so this is roughly what we've talked about so far. Lots of NP hardness results. And then I've briefly mentioned, I think I forgot to mention this top result that Joe with David and Tom in an unpublished paper proved that push *F is actually PSPACE-complete. And then we have Sokoban is PSPACE-complete. What about all these other versions? What about push 1? Push 1. Certainly if you add the X, the problem is in NP, so we're kind of done. But without the X, which of these problems are PSPACE-complete? We know some of them by now, but not all of them. So the first results that came out in this area are these bottom 2. So the first result is that push 2F is PSPACE-complete. So this is strength 2 or larger. There are fixed blocks, no sliding. I just want to get from start to finish. And for push 1 or push *F, these are also PSPACE-complete. 2 different proofs for this. But they're based on non-deterministic constraint logic, which you may have seen me talk about before or read this book, Games, Puzzles, and Computation. Truhe translated. So brief recap, you have a machine which is given by a graph with blue edges. Blue edges are worth 2, red edges are worth 1. And you have this, a state of the machine is going to be an orientation on the edges. And the main constraint, or the only constraint, is that every vertex has at least 2 units of incoming value at every vertex. So for example, at this vertex, there's 1 unit coming in from here and 1 unit coming in from here. At this vertex, there's 2 units coming in from here. So that's enough. At this vertex, there's 2 units coming in from here. You can have more, but you have to have at least, for example, this one has 1 unit coming in from here and 2 from here. As long as it's at least 2 at all times, we're happy. And we actually only need 2 types of vertices. There's this AND vertex where you have 2 reds coming in and 1 blue. It's called an AND because this edge can point out if and only if this edge is pointing in and this edge is pointing in. You need the 2 reds to equal 1 blue. And we also have an OR vertex, which is just 3 blues. So in this case, at least one of these blues must come in, so it's like an OR of 3 things, or 2 things, depending on how you look at it. And the moves you're allowed to do in non-deterministic constraint logic is pick some edge and flip it, as long as flipping it preserves that this invariant holds. So very simple, and this turns out to be PSPACE-complete. So like deciding, given an edge, deciding whether it could be flipped is via sequence of flips is PSPACE-complete, even if you have a planar graph, so you don't need a crossover gadget, and even if all the vertices are ands and ors. This is with Bob Hearn. One of the first things we did with this technology was give a simpler proof that Sokoban is PSPACE-complete. So here, this is, I think, the first time this proof has ever been animated. So I'll let you stare at it for a little bit. But we are implementing an AND gadget on the left. So if this can be pushed left and this path can be pushed up, then it's possible to push this C path to the left. That's what this is showing. But if only one of them pushes, you can't push this to the left because you would get stuck in here. Or the block would get stuck, and all of these blocks are actually in the position that they're supposed to be, except for one at the very end. And so you really can't get a block stuck in a position other than where it starts. And in this example, I think we're pushing this up, which lets us push this to the left. Cool. So that's second proof of Sokoban. I think we'll see one more later on. Here, very quickly, is a proof that push-1 is PSPACE-complete, also using non-deterministic constraint logic, though this is not how we ended up writing it in a paper. Maybe this came later. I forget. I don't think we ever wrote it, but I did make PowerPoint animation for it back in 2004. So I have that. So when 2 blocks come in, then a third one can go out. And for push-2F, we had an even more complicated reduction from non-deterministic constraint logic, but it's possible. So this was the status of pushing block games for a while. That we had these NP hardness results for the regular push-K, push-star. For push-push, we knew PSPACE-completeness except for star. For Push-1F in particular, we had NP hardness, but we didn't know about PSPACE hardness. That's actually the main result I want to tell you about today, is that this one is PSPACE-complete. That's the new result this year. The things we knew were PSPACE-complete were Push-2F and higher, not Push-1, and Push-F, and yeah. Cool. So this is pushing blocks. I want to take a little diversion and talk about other things you could do. One is that you could switch to the Sokoban goal of storage. Maybe you have n spaces, you want to put the n blocks. Most of these variations of push have not been studied. Of course, there's Push-1FS, which is exactly Sokoban, so that proof applies. But there are lots of others here. There happens to be an NP hardness result that works, but it seems most of the others are open. I suspect these are not too hard to solve, because usually storing is a harder version, but it doesn't obviously follow and could be interesting to think about. The other thing that's been studied is pulling blocks. This has been looked at a lot. In particular, I'm citing 2 of the early papers here, just not too long ago. You'll see a bunch of variations. There's pull. It's pull question mark. I'll talk more about that in a moment. But pull is exactly the inverse of push. So when you walk up to a block, you can, if you want, you can pull it backwards instead of pushing it forwards. In pull, you can't push. In push-pull, you can both push and pull. There are a lot of video games that work this way, like what am I thinking of? Portal, for example, especially 2D Portal, you get pushing and pulling blocks. There's pull-pull, which is like the opposite of push-push. There's push-push-pull-pull. And I think those are all the variations you can do. So a lot of these have been solved to be PSPACE-complete. There are 2 here that are open, but the asterisk means we solved them later. So I'm going to start by just showing you, and then all these problems are open if you don't allow fixed blocks, I believe. I'll show you just one of those proofs. This actually applies to a lot of different cases. It's a p-space-completeness proof. It's again from non-deterministic constraint logic. So NCL is a useful tool in many cases. But there's another natural version of pull. This comes up in Baba Is You, for example, a very nice puzzle video game, recent. With pull question mark, you get to choose, for example, when the robot moves up here, it does not pull the block. So usually in the game, this is implemented by holding down a key or pressing a button to say that I want to pull. In pull exclamation mark, you must pull all the time. So now when the robot moves up here, the block tails behind. These are two versions. The version that's been studied before is pull question mark. That's the opposite of a push. What we did in a recent JCDCGGG paper, actually, which you may have seen it there, is both settle the complexity of pull question mark for finite and infinite strength pulling, and also settle the version where you must pull all the time. So we proved all of those are p-space-complete. Here is an example. Here's that proof. This covers, I believe, all 4 cases at once. And it's, again, a reduction from non-deterministic constraint logic, similar to the Sokoban proof, but now with pulling instead of pushing. So there are these blocks which can move between 2 possible positions, and the fact that these areas have to not be cut off, or else the robot gets stuck when you're pulling, prevents you from violating the constraint at each vertex. Okay, one last variation of all these games, push and pull, is you can add gravity. This is common in Balderdash, for example. If there's blank space underneath the rocks, like there is here, this guy's actually about to fall down, it will fall straight down. In Balderdash, there are some other weird physics rules, but pull G for gravity means that the blocks fall. And you see, as soon as the robot pulls this to the left, for example, the block falls all the way down. It's kind of instantaneous, so it's a little hard to see. Again, our goal here was to introduce a version of this puzzle that is easy or easier. In particular, it seems like almost every move you make in pull G, a block falls down and it can never go back up. So you think that this problem is in NP, right? Actually not. It turns out all of these games, except for one case where we can only prove NP hardness, we can prove all of them are p-space-complete. So the one open case is pull question mark 1FG. So G means gravity, F means there are fixed blocks. You can pull strength 1. It's question mark, so you're not forced to pull, but you have gravity. That version we can prove NP hard. Once you get to strength 2, or you have thin walls, or you have forced pulling, or you have infinite strength, all of these we can prove p-space-complete. For fun, let me show you the NP hardness proof. This is the NAND gadget. Remember the NAND gadget from 1999 or 2000? Now that we know more recently that that one gadget alone is enough to prove NP hardness of your reconfiguration problem, we found a way to build that in pull question mark, and then we are done. We know this problem is NP hard. For the p-space hardness proofs, we need another framework. These are not going to be based on NCL. Now they're based on this newer framework called the gadget framework, which I highly recommend if you have an agent-based game where you're walking around, sort of designed for that. Here's an example of a gadget in this framework. It's called the locking 2 toggle. It has the property that if you can walk along the arrows in the indicated direction. When I traverse one of the arrows, that arrow reverses and the other one disappears. So that means the next thing you have to do in terms of this gadget is go backwards along that arrow that you just did. You could later traverse the other arrow to the right, and then you must later traverse it back to the left. So this is represented by this diagram over here. There are 3 states: neutral, up, and down. In the neutral state, you can follow this path, and you will transition to the up state, which has one available traversal backwards along the edge you came, and then you will transition back to the neutral state. And similarly, if I go along this path, it says I switch to the down state, which is this one, and if I go back here, I go back to the neutral state. Okay, so in general, a gadget has locations. That's these corners here where you can enter or exit the gadget. It has some finite set of states, in this case 3. Oops, sorry. And it has allowed, in each state you have allowed transitions, and that may also change the state. It's basically a finite state machine, but with some geometry. And then you're given a network of these gadgets and their initial states, and you want to know, is it possible to get from some start location to some goal location via a sequence of traversals through gadgets? Sometimes this problem is easy, but most of the time it's PSPACE-complete. There's this nice characterization, this is with Dylan Hendrickson and Jason Lynch from 2020, that in a certain family of gadgets, which I won't define here because I don't need it, reversible deterministic tunnel gadgets, these things are called tunnels, that we have a characterization. Motion planning through a bunch of these gadgets is PSPACE-complete if and only if you have at least one gadget with interacting tunnels, meaning that traversing some tunnel affects the traversability of another tunnel. That's all you need for hardness. And this is if and only if, so it, in some sense, characterizes all gadgets that are hard. In fact, this locking two toggle is kind of fundamental because you can show that all gadgets simulate it. And if it's not PSPACE-complete, it's polynomially solvable. All right, and fun fact is that you can add planar in front of this statement. And so that means you never need a crossover gadget with this framework. Using this theorem, you know that you can assume the connections between the gadgets are planar, non-crossing. And in fact, one of the early applications we had, this is even before the 2020 paper, of this gadget framework was to prove that 3D push-pull 1F is PSPACE hard. This has since been superseded by the other results I showed you, but it shows you can build something nice relatively easily in this model called a two-toggle, which is PSPACE-complete. Okay, but in the non-subsumed results, we have this version, pull $2FG. Remember the 1F we proved NP-hard. So this is an example. You'll notice that even with gravity, these blocks never fall. And so we never lose vertical entropy, I would call it. And it turns out we can build roughly a locking two-toggle. It's a slight variation called a non-deterministic locking two-toggle. But I won't go into the details here. With these pulling two blocks at once, you can actually build these gadgets and get hardness, PSPACE hardness. So I believe I've shown you these results in this pull framework, the NP hardness, and the one I just showed you covers these three cases. I'd next like to talk about these results, which use another framework, a variation on the gadget framework called the door framework. Door is just a type of gadget. This fits into the gadget framework I just described. But I guess it was developed earlier by Giovanni Viglietta for analyzing lemmings, and then we used it for proving Super Mario Brothers is PSPACE-complete. So it's a gadget. It has two states, open and closed. If you traverse the open path, you can open it if you want. If you traverse the closed path, you must close the door, and if you can follow the traverse path only if the door is open. And there are actually a bunch of variations. The open path could be optional or it could be forced, doesn't really matter. And each of these paths could be directed, say left to right, or a mixture, or they could be undirected. You can traverse them in both directions. Okay, so there's some finite set of doors here, door gadgets. Here's an example of a door just to give you some like concrete feel of how they work in not Sokoban, but Sokobond. So these are bonds between atoms in a molecule, and it's going to move as a rigid object. So for example, in this case, it's impossible to move to the right here because these are fixed blocks. But if I come in and open this gadget by moving that module down, then I'll be able to freely traverse. And on the other hand, if I have to go through this tunnel, I am forced to close the door. I can open it again and so on. Okay, here's another type of door, self-closing door. Basically take the door and wire the output of the traverse to the input of the close. So this is basically saying there are two ways to traverse this gadget. Open, just like before, will open the gadget if you want it to. And self-close. This is possible only if you can go through this path only if the door is open, because you need to do this traverse through the door, and then you must close the door afterwards as you exit, kind of self-closing door. Here's an example of how to build that in Sokoban. If I come through this traversal, I am forced to close the door. I could later come and open it here, just like before. And one more door type is the symmetric self-closing door. So this is nice because the state diagram here is completely symmetric. There's actually no difference between open and closed here. They're just words. In the open state, you can follow this close path, and you close the gadget, so you switch to the closed state. In the closed state, you can follow this open path, but not the closed path. So these two, basically it's alternating between I can go on the bottom edge and I can go on the top edge. Every time I traverse, it switches edges that I can traverse. Here's an example of building a symmetric self-closing door in Sokoban. Sokoban is a nice playground for building these kinds of gadgets. So that was one of them, I guess, self-close. And then here's the other one, self-open. This is a directed symmetric self-closing door. Okay, turns out all of these gadgets are PSPACE-complete. If you can build any one of them, then deciding whether you can go from start to finish, given a planar, or given a network of those doors, is PSPACE-complete. In fact, door gadgets are universal. They simulate all gadgets, but I won't get into that here. For the planar version, it's funny. Every single door, except for one of them, this nasty door here, is PSPACE-complete. So we can avoid crossover gadgets in those cases, except for case 8, though recent work maybe finally fixes that door. Okay, here's an example of building a self-closing door in pull exclamation. This was forced pulling with strength 1, fixed blocks, and optional gravity, because the blocks will always be protected below. So the key picture is this one. That when the robot comes in here, if they want to go down here, which is the only way they'll be able to go, because it's forced pulling, this block gets pulled to the left. So that's the self-close operation. And then the open is easy. You just come in and pull the block back. And you have this little kink to let you leave without pulling a block with you forever. So it turns out to be a really simple proof once you have this infrastructure, which is sort of the name of the game here. We're building up hardness tools to make it easy to analyze all these kinds of puzzles. All right, so this is the state of results that I've shown you. Okay, end of pulling blocks, back to pushing blocks. I want to talk about one last thing, which is this result, Push-1F, the original game, more or less, that we analyzed. We proved NP hardness back in 2000. Now, a new result this year at Fun is that it's PSPACE-complete. So I want to show you that, tell you how we did that. This is 24 years later, 22 years later, something. A lot of years. Amusingly, we're going to use a 24-year-old result, Culberson's proof that Sokoban is PSPACE-complete. So it turns out there's a way to make this work, though it requires a lot of work. So here's a simple gadget. It's intended to be a one-way from this direction to that direction. And if you use it correctly, like in this picture, it works great. In particular, if this block stays on this little track, the blue segment there, everything is happy. The problem is there's another way to use the gadget, which is you push the block into the corner. Now it's permanently open, and it's a useless gadget. So we call this breaking the gadget. In Culberson's Sokoban proof, you can prevent this by saying, well, the block has to end up here. And so if you ever wedge it into the corner, you're never getting it out. So you will never wedge it into the corner. With Push-1F, which is almost the same game, it just doesn't have these storage locations. It's just the goal is to get the robot to a particular place. We don't have this luxury. So we're going to do some other tricks. We're going to define this gadget to be broken whenever the block is off the track, and we're going to observe that once the gadget is broken, it stays broken forever. That will turn out to be enough to prevent it. Here's another gadget. We're going to need, I think, 3 gadgets in all. Next 2 are almost the same. This is a one toggle, so it's explained by this state diagram. In the left state, you can move to the left, and then you switch to the other state. In the right state, you can move to the right, so they're directed paths. And each time you move, it switches directions. And so this looks good. You know, the gadget is supposed to work this way, And as long as the blocks don't get stuck in the corners, and as long as they don't get stuck next to each other, then this gadget will indeed work like a one toggle. But if you, and with Sokoban, you can specify locations and this all works, but in Push-1F it doesn't. But we're going to make it work anyway. And if you take the same gadget and you add a hole up here, this turns out to be really useful. It's called a precursor, or we call it a precursor. Culbertson didn't give it a name. It's not explicitly a gadget in his construction, but it's sort of in there. This gadget behaves the following way. I'm going to rephrase. It's similar to the one toggle, but when you enter this gadget, either from here or whatever, if you exit through the bottom, you have to push the blocks away from that exit, which prevents you from, so if I exit here, if I last exited on the right, it will be impossible to enter from the left, and vice versa. So it remembers the last lower exit, you can't enter at the other lower exit. And you can always get to the top. So it turns out, if you take these three gadgets, if you remembered them, we can build a self-closing door. Culbertson didn't have self-closing door technology at the time, but he built this gadget anyway. Here it is in Sokoban land. So if you take a diode, the first thing I showed you, and you combine it with a one toggle, which was the second thing I showed you, and a precursor and another diode, then it turns out this is a self-closing door. Let me show you. So if we enter the gadget here, we're forced to enter from the left. Then we enter the precursor gadget. That we can't go up here because of the one toggle, so we have to go to the right. Because we exited on the right here, this gadget switched to the state where it's impossible to re-enter here. And then we can exit the gadget. So now if you try to come in again, you get stuck. So that was self-close. We could traverse it because the gadget was open, but then we closed it while we were doing so. On the other hand, you can open by entering at the top. If you come down, this one toggle will flip around. Now, where do you exit? You could go to the right, but if you do so, you will never be able to re-enter this gadget because this is blocked and this is blocked. So it's kind of a broken state, and in Sokoban, you can prevent those. The intention is that you go to the left, which resets this gadget to the pointing right, and then you exit back on the top, because you can always get to the top. So this opened up the door again. So this is a self-closing door. So what's cool here, so one fun thing, this is our third proof that Sokoban is PSPACE-complete. The old proof is on the bottom here in gray. The new proof is this gadget. Once you realize that gadget is a self-closing door, you can use our self-closing door technology, and boom, you've got PSPACE-completeness. Whereas you don't need a crossover, you don't need to build a Turing machine. All right, now I claim that we can make these gadgets work for Push-1F. What I'd like to do, going back to this diode here, it's supposed to go one way from here to here, I want to force the block to stay on the track like the top diagram and not get stuck in a corner like the bottom diagram. So what we're going to do here, let me show that again, we're just going to focus on the top three rows, erase the others for now. And we're going to draw these two arrows. These are special check traversals. It's possible to do this arrow and then this arrow, if and only if we're in a good working state like the top. The block is on the track. If the block is stuck in a corner, you won't be able, if it's stuck in this corner, you won't be able to do this traversal. If it's stuck in this corner, you won't be able to do this traversal. When I say this traversal, I mean enter at this entrance and exit at this exit. So the idea is, let's force the robot to perform some specified traversals at the very end of the construction before reaching the goal, and thereby check that the gadgets aren't broken. So here's a framework for doing that in one slide. It's a very powerful framework. Instead of building a gadget, we're going to build a checkable gadget, a checkable version of the gadget. What we'd like to build is this G where the block is forced to stay on this track. What instead we're building is this G prime where the block could go anywhere. But at least at the end, we could draw these check traversals. So we're going to take a gadget G prime that we can build. We're going to take a sequence of check traversals, and we'll call a state of this gadget good if it's still possible to do the check traversals, and broken if it's not, if some of the traversals aren't possible. And what we need is that once you're broken, you stay broken. So closure. Then we will say that we have a checkable G if when we take this gadget, we restrict it to the good states, we get G. This is called post-selection. And I'm running low on time, so let me just say the theorem that if you want to do motion planning with gadget G, this is the thing that we want to build and we know is hard. We can reduce it to motion planning with this G prime together with a couple of small gadgets, which are relatively easy to build. So in some sense, we can pretend that we built G, even though we didn't. We built this G prime that can break as long as we can build these gadgets that let us check it later. This is the proof. It involves adding some paths here to do all the checking and some special crossovers that we show how to build. Now let me show you how it works. Like if we take this gadget, which we know how to build, together with these traversals, and we do this post-select operator, we get this gadget where the block is forced to stay in the middle. And then if we connect these two paths, we get our diode. Magic. Let's do it again. Let's do it for the precursor. So I want to build this gadget at the bottom where these blocks never get stuck. So we're going to take the bottom 3 rows, and we're also going to add these extra connections just because we need them. And we're going to say, let's at the end check these two traversals. That will prevent any block from being stuck in here and any block from being stuck in here. So if we do this post-select operator, we force the blocks to be in this middle part. Let's do it again. I'm going to do add this check traversal and this check traversal. If we do a post-selection, this will prevent these two blocks from being next to each other. If they were ever next to each other because we're strength 1 here, you'd get stuck. So now we can force the blocks to not be adjacent, and that is the working structure. We just add the rows that were missing before, and we have our precursor working in Push-1F through checking. There's one more thing you may recall. I could exit the gadget in an unintended way here. No problem. Just add another traversal for checking and do post-select, and now you'll be guaranteed that never happens. It's a super powerful hammer once you have this checking gadget. Now we have proved Push-1F is hard, provided we can build this simple gadget called a single-use opening gadget and this merge single-use closing gadget. Turns out it's a little bit of work, but it's not that hard because you'll see, for example, this no return gadget from 2000. We get to use it again. It's at this point, even though we're proving PSPACE hardness, we can build gadgets that only work once because we only check one time at the end. So this is relatively easy to do, though it's still a bit of work. So that is the PSPACE-completeness of Push-1F. Open problem is removing this F, although I think we have solved that. Haven't finished it yet. The bigger open problems are push star. Is that PSPACE complete or push star? These seem like they're probably NP complete, but I don't know. And just briefly mention, there's a new draft of a book to come out in 2024 with MIT Press about hardness. It has not a lot about the gadget framework, but it does have a bunch of the early pushing blocks hardness proofs, a lot of NP hardness, PSPACE hardness, and other good stuff. It's free online. You can take a look and please send us your comments. And that's pushing block puzzles. Thanks.